Hello, students, and welcome. Have you ever followed a recipe perfectly, but the final dish was something completely unexpected? Well, something very similar can happen in chemistry. Today, we're going to investigate a very fascinating puzzle called abnormal molar masses. So, let's start with a simple question. Now, you all remember colligative properties, yes? These are the properties that depend only on the number of solute particles, not what they are. We have a very reliable formula for one of these properties, freezing point depression. But look, when we use this formula for a simple salt solution, the result is, well, it's strange. The measured freezing point is almost double what the formula predicts. For example, a 1 mol NaCl solution should freeze at minus 1.86 degrees Celsius, but in reality, it freezes near minus 3.72 degrees Celsius. So what is happening here? The secret, you see, is not that our formula is wrong. No, the formula is fine. It's our assumption about the solute that's incorrect. Let's find out what's really going on inside that solution. Think about it. We put in 1 mole of salt, so naturally we expect the effect of 1 mole of particles on the freezing point. But the solution is behaving as if we have added 2 moles of particles. This difference, this gap between expectation and reality, is the main point of our mystery. You know, this isn't an error in our experiment or a mistake in our measurement. It's actually a clue. The colligative properties are telling us the truth. They are showing us the actual number of particles floating around in the solution, which is different from the number of molecules we thought we added. To really understand this, we need to zoom in and look at what the solute particles are doing at the molecular level after they dissolve. It turns out there are 2 main things that can happen. Let's use an analogy to make this crystal clear. Imagine you are organizing a big conference, okay? And you're trying to calculate the cost per person. But the number of people can change based on how they behave when they arrive. So let's say a solute molecule breaks apart. That's like one attendee who bought 1 ticket suddenly splitting into 2 people. In chemistry, we call this dissociation. Now, what if 2 molecules stick together? That's like a couple arriving together and acting as a single unit. We call this association. You see? In both cases, our final count of particles is going to be different from what we started with. So the first behavior is dissociation. This is exactly what happens with salts like NaCl. You put in 1 formula unit of sodium chloride, but in the water, it breaks apart into 2 separate ions, 1 sodium ion, Na+, and 1 chloride ion, Cl-. So 1 unit becomes 2 particles. This directly increases the total number of particles in the solution. And the opposite behavior is association. This can happen with molecules like acetic acid when they are in certain solvents. They can form hydrogen bonds and pair up, creating a larger unit which we call a dimer. So here, 2 separate molecules become just 1 particle. This, of course, decreases the total number of particles. Okay, so we know what's happening, but how do we fix our calculations? Well, back in the late 19th century, a brilliant chemist named Jacobus von Hoff came up with a very elegant solution for this exact problem. He introduced something called the Van 't Hoff factor, and we represent it with the letter I. It's basically a correction factor. It's a simple number that tells us the ratio of the actual number of particles in the solution compared to the number of formula units we dissolved in the first place. It's very straightforward. For a solute like glucose, which just dissolves as 1 single molecule, I is simply 1. For NaCl, which we know breaks into 2 ions, I is 2. And for something like calcium chloride, CaCl2, which forms 1 calcium ion and 2 chloride ions, that's 3 ions in total, so I is 3. It's just a count of how many particles each unit forms in the solution. So here is the most crucial point to remember for your exams. When dissociation happens, there are more particles. This leads to an abnormally low measured molar mass. Why? Because the total mass is now divided among more particles. And when association happens, there are fewer particles. This leads to an abnormally high measured molar mass, because the same mass is divided among fewer but larger particles. But you might ask, sir, why does this really matter outside of our chemistry lab and exams? Well, this concept has some very critical applications, where getting the numbers right is extremely important. Let's take a very serious and important example, the saline solution that is used in hospitals for IV drips. The chemistry here is literally a matter of life and death. You see, for a saline drip to be safe for a patient, its osmotic pressure must perfectly match the osmotic pressure of our blood plasma. This is to make sure our red blood cells don't burst or shrink. And this calculation is correct only if we account for the fact that NaCl dissociates into two particles. That is, by using a Van Hoff factor I equals 2. If we didn't do this, the solution would be completely wrong and could be very harmful to the patient. All right, that was a lot of information. So let's just quickly recap the main points from our discussion. First, remember that the molar mass we calculate from colligative properties can seem abnormal. This happens when solutes either dissociate, which creates more particles, or associate, which creates fewer particles. And second, the Van Hoff factor I is our simple tool to correct our formulas for this real-world behavior. To become comfortable with this topic, just remember that conference analogy we discussed. Before you start solving any problem, always ask yourself one simple question. What is my solute actually doing in this solution? Is it breaking apart? Is it sticking together? Or is it just staying as it is? Answering that one question is the key. You see, an abnormal measurement isn't an error. It's actually a window that lets us see into the molecular world. It tells us how particles are truly behaving in a solution. And when you understand that, the math becomes easy and the topic becomes intuitive. So next time you see an unexpected result, remember, it's not an error, it's a discovery. Keep up the good work.